Hello and welcome to CE 5331 Probabilistic Methods for Civil Engineers. My name is Venki Adamari. I'm a professor in Civil Environmental and Construction Engineering here at Texas Tech University. And in this lecture, I'm going to give you a brief introduction of the class and cover some basic understanding or provide a basic understanding of probabilistic methods. So to begin with, let's talk about probability and civil engineering. Okay, so probability, if you've taken a class in statistics or learned about probability in your high school, we always talk about, rolling dice or flipping coins or picking colored balls. So a lot of those examples that you've seen probably deal around those types of random events. But probability is more than just rolling a dice or picking up colored balls or flipping coins. Probability concepts are used extensively in civil engineering analysis and design. So a big part of this course, or the purpose of this course, is to take an in-depth look at probabilistic methods, namely what are some of the common ways to describe probability, how do we take real-world data sets and fit those data sets to probability models, and then how can probability be used for analysis and design of civil engineering systems, namely how can we use probabilities to calculate risk, assess reliability, assess resilience, vulnerability to failure, and those kinds of things. To learn these concepts, we'll make use of the R programming environment. R is an industry standard software for performing probability and statistic analysis. So one of the good byproducts of this class is that you will be learning, in addition to concepts of probability and how they apply to civil engineering, you'll also be learning an industry standard software, R, which is used extensively for data analysis. And it's a great software, a free software for using, for performing data analysis and a whole host of other things that you can do with R. And as part of this class, you will also be putting to use the probability concepts that you learned in this class on a data set that's of interest to you. So you'll be doing a semester-long project to understand and reinforce the concepts that we've learned in the class. So role of probability in civil engineering. Civil engineers, as you know, work in the nature. So either we design structures or we analyze natural phenomena. So invariably there is a lot of natural variability and uncertainty in various disciplines of civil engineering. So regardless of what you're studying in civil engineering, you will find uncertainty and variability in the data sets that you collect. For example, here I show the mean black carbon concentrations that a set of researchers measured over a period of time, and you can see that the concentrations of these black carbon aerosols, which are fine particles in the atmosphere, like the soot particles in the atmosphere, you see that they vary quite a bit. So, and not only do they vary within each month, but you will also see some sort of a variability across different times of the year. So sometimes that variability is high, sometimes the variability is low, sometimes the concentrations are high, sometimes the concentrations are low. But in general, you will see that there is really no single value, or there is no easy way to predict these concentrations. Another example, if you look at geotech, here I'm plotting undrained shear strength and in kips per square foot across the depth. This is data collected for the San Francisco Bay mud, and at a site in San Francisco. This is data coming out of Duncan and Buccigiani in 1973. And you will notice that the two lines here, the highest concentration and the lowest conceivable, are theoretically what data we can think as we go down. And those data points, which are the circles, vary quite a bit. So there is an average value, average plus or minus standard deviation, and you will see that many data points fall in that but there is also variability at a given depth. So if I take a depth of 50 feet, you will see that the values can be anywhere between 0.1 to about 0.6 kips per square foot. So there is quite a bit of uncertainty and variability as we go to different depths, as well as at a given depth. There is quite a bit of variability that you will see. So geotech engineers who deal with soils deal with a lot of uncertainty as well. If you go to structures, wind loads tend to be proportional to the square of the wind speed. And again, this is what's called as a windrows plot. It shows that the winds blowing from different directions. And also for a given direction, say winds blowing from the south, you do see that there is quite a bit of variability in the speed of the wind at that site. So this could be data from over a year, and that again shows that the winds do vary at different times of the year, within different times of the day, and even for a given wind direction, the wind speeds can fluctuate considerably. Water resources, this is showing water resources data from stream flow in the American River in California. And again, you will see these huge peak flows, which are the flooding events, and then you will see periods of low flows, which correspond to droughts. So the ebb and flow of the river, which are the floods and the droughts, create considerable variability. Again, we are plotting over different years, and if you look at 1998 versus say 2000 and 2002, there is quite a bit of interannual variability in that stream flow. So again, if you're dealing with water resources systems, be it surface water, groundwater, you do see variability in your data. So regardless of what discipline of civil engineering you're interested in, you will see variability. Again, here I'm showing you transportation example, which is the vehicles per minute that is collected over about a little over 2 hours, and you'll see that at this intersection the vehicles per minute vary quite a bit, both in the short intervals as well as over that hour and a half 2 hour plus duration that we are showing here. So regardless of the discipline, you're going to see variability, and what probability does is it provides us with a language. It provides us with a language to analyze this type of data and get insights from this type of data that we can then use to design our systems so that they can work or function across the variability that we see in our systems. So probability is really the fundamental language to describe uncertainty and variability, and getting a good sound understanding of probability is essential regardless of which discipline of civil engineering you're going to be studying, because there is uncertainty and variability in all that we do as civil engineers. Talking a little bit about future of civil engineering, you probably have heard about concepts like big data, cloud computing, sensors. So civil engineering data is becoming available at an alarming rate. And a lot of that data, because of internet, is now readily accessible. New sensors help us collect data much more quickly and much more efficiently. And then we have cloud services where data can be stored and disseminated worldwide. So big data is an umbrella concept that looks at all these things, and civil engineering big data often has several characteristics. One is that there's a large amount of volumes of data that are available, hundreds of gigabytes to petabytes type of data that are being available now for various applications. The speed at which the data is coming in is also getting very quick, because we have automated sensors that can take data at milliseconds or even less, so at very, very high frequencies. The data is also becoming available in a variety of different formats. So all of us carry cell phones, we click pictures, we take videos, we can record audio, so, and then there is a lot of unstructured data like text data, reports, or graphs that can be analyzed as well. So variety of the data, and of course the quality of the data is a very important factor. So as we collect data at very high frequencies, oftentimes there is uncertainty in the data. We are able to characterize that variability in the data. So the quality of data, the variability of the parameters, characterizing that uncertainty in the data becomes very important, which again is where probability or the concepts of probability come in very handy, or the fundamental building blocks for looking at data that exhibit variability and uncertainty. And of course, as civil engineers, we want to extract as much value as we can from those data. And if we have uncertainty and variability in our data, really the probabilistic tools help us collect that data efficiently and analyze that data efficiently. You may also have heard of a lot of new technologies like artificial intelligence, machine learning, and other data-driven computational methods that are already playing a role, and these types of models are going to play a much bigger role in our engineering design and analysis in the future. Again, if you want to understand machine learning, artificial intelligence, or other data-driven models, you need to have a sound understanding of probability, because a lot of these techniques build on probabilistic concepts or methods of probability. So again, if you look at data that civil engineers collect, there's going to be uncertainty and variability. If you look at the volume of data or the rate at which the data is being collected, we are going to be able to better characterize variability and capture that uncertainty in your data, which means that again probability plays a very big role in analyzing big civil engineering data. And if you want to use new and latest and greatest data analysis tools like machine learning, artificial intelligence based techniques, then understanding probability is very critical. So hopefully I've convinced you that we need to be, there is reasons for studying probability. Clearly, your knowledge of probability, or your understanding of probability, is the key to understanding better, civil engineering data, using new techniques to analyze civil engineering data, and do other advanced analysis and design with civil engineering data. So with that, I'm going to talk about the second part of the class, which is how we are going to be learning. So obviously I'm going to teach you a lot of theory associated with probability and probability models. But as engineers, theory for us plays a secondary role. We need to understand the theory so that we are able to extend what we learn to newer problems. But we also need to understand and learn hands-on tools where we can actually do data analysis. And for that, I'll be using what is called as the R statistical programming environment. R is a versatile software, and the best of it is it's free. It's got a lot of tools for calculating probabilities, but also do other things such as statistics, machine learning, solving differential equations, mapping, visualization. So R is really a great software, a one-stop stop if you want to learn to do data analysis. So we'll be emphasizing R and using R to do data analysis in this class using probability models. And R has great visualization tools for charting and graphing. So presentation of data becomes very easy with R once you get the hang of it. And R can produce very high quality publication graphics. So if you're a PhD student or a master's student looking to publish your data or publish your report, publish your thesis, R can provide you with excellent tools to look at your data, slice and dice your data, and visualize it in many different ways. So again, so investment in learning R is not just useful for this class, but also useful for you lifelong as you go and practice engineering as consultants or in academia or elsewhere. So spending some time learning R will have a great payoff in the future. And then R, of course, can be used to automate tedious calculations. So it provides you with the rich tools of structural and object-oriented programming. So R can be used to make thousands of calculations, or tens of thousands of calculations fairly easy, or make it very easy for us to do those types of calculations. So I'll show you some examples of that as we go along in the class. Okay, and R works with a variety of data types and structures. So if you have discrete data, like say count of vehicles at an intersection, or whether you have a continuous data such as flow rates in a stream, or water levels, or strains that are measured on a bridge. Those types of data, or a variety of different data, can be analyzed using R. So R again gives you a lot of flexibility. So some investment into learning R is good. And of course, the downside of this is R is not like Excel or Word or other Windows-based programs that you're used to, where you have menus, you can drag and drop and do things. You will have to write some short programs, which are called scripts, to do your tasks. And of course, this may seem intimidating at first because there is no nice graphical user interface associated with R. But the concepts that we're using is not completely new. It's very similar to what you have seen in ENGR 1315. If you've gone through the Texas Tech System civil engineering program, that's a required course on programming, freshman level or first year level programming. You probably have had similar classes if you've studied civil engineering elsewhere. So again, if you don't remember, it's been a while. It's been a while since you've written a program or seen a program. No worries. I will provide code for most of what we do in this class, and go over it in the class, and I will annotate the code, provide comment lines so that you can see the logic of what's going on. So it's not like you will be thrown and asked to swim with the sharks, but sometimes it may feel like it, even though I'm giving you a lot of code. But if you do persist, the payoff will be good. Having programming skills gives you several advantages. It makes you think logically. So at the very least, even if you don't program, it makes you sit and think what are the steps involved for doing analysis, which is a great thing to have as an engineer. It helps you automate tedious calculations, expands your ability to do more complex analysis. It helps you learn new techniques, especially AI and machine learning, and other things that you may have to learn in the future as civil engineering, or the practice of civil engineering changes. And of course, if you can make fancy graphics and good visualization tools, that's a neat way to impress your boss and your advisors, and ask for a raise. So eventually there is payoff associated with knowing programming. There are some really good blogs out there for reasons telling why you need to learn programming and why you need to learn R. I've given you 3 such websites that you can go and look at your leisure. You don't have to take my word for it. You can see what the other bloggers are saying about this as well. There are many companies that use R. Ford uses R to improve its design of its vehicles. Twitter uses R to monitor user experiences. The National Weather Service, a government agency, uses R to predict flooding. Human Rights Data Analysis Group uses R to quantify the impact of war. R is used in New York Times. So if you've read New York Times and seen some of the infographics, they're being generated by R. Google uses R. Facebook uses R. So if you've used Google, Facebook, read New York Times, or looked at National Weather Center, you have already seen the advantages, or used Twitter, you probably have seen the advantages of R in providing a good user experience, or in providing the data analysis that are necessary. So we are in the league of all these people who are using R. So that's a good thing. And of course, just like anything else, the more you practice, the better you become with programming in R. So I would strongly encourage you to, not shy away from programming, and not be afraid of making mistakes and learning from those mistakes, because that is the best way to learn in the long run. It sucks in the short term, but definitely a really good way to learn and remember things in the long run. So how is this class structured? Of course, my basic goal of this class is to help you understand basic concepts of probability. I want to show you how probability concepts are useful in civil engineering. I gave you some examples early on, but we want to build on that. And we want to look at some probability-based techniques and concepts that are used in civil engineering, things like risk and reliability, resilience of systems, using Markov chains to make predictions, using queuing theory to understand the dynamics of how certain systems, work. So in addition to providing you the theory, I will also be giving you some application examples, throughout the course of the semester, where you will see how the concepts that you've learned in this class, or the theory that you've learned in this class, can be used. So we'll blend theory and practice, and we will use real world data sets, because real world data sets is what you'll be analyzing as engineers, whether as part of your research, as part of your consulting practice, or excuse me, wherever you tend to go. So we'll be giving you a first glimpse of using real world data as opposed to a textbook example for solving problem. This is a course called Probabilistic Methods for Civil Engineers, so I will try and provide examples from all disciplines in civil engineering: transportation, structures, geotech, water resources, environmental, water resources, environmental. Did I say water resources and environmental 2 or 3 times? Yes, that clearly is my bias. That's where I've used these techniques for the most part, so you might see my bias show up once in a while, but I will do my best to give you examples from all disciplines. And again, you might be interested in a specific discipline, but seeing examples from other disciplines that are not your area of study gives you ideas. A lot of times may give you good ideas on about your own research and own analysis. You might say, hey, this is cool. This is what the transportation engineers are doing. Maybe I can take that and apply it to my water resources problem. Or this is how the water resources people are looking at their hazards. Maybe I can extend some of that ideas to structural understanding structural hazards or construction hazards. So there is a benefit to looking at disciplines outside of your own, or looking at what's happening in disciplines outside your own. So that's kind of one advantage of trying to teach this class on a more broader scale, as opposed to teaching it in a focused discipline-specific manner. So that's how we have structured this class. And again, the way I typically structure my classes are using what's called as the Bloom's taxonomy. And Bloom's taxonomy tells us basic levels of skills that we need to have as part of our learning. So we start off with remembering things. These are very basic concepts that you need to know, that you need to recollect and you need to remember. Those concepts, you need to show that you can understand these concepts. And for engineers, it's not simply important that you understand what the concept means, but you should be able to apply that concepts to problems of interest to you. And then once we apply these tools and models, probability models, you need to know how to analyze that data, and then evaluate and make decisions on what does it mean to my design and to my analysis. And eventually, as the highest level of learning is to basically create new knowledge, and then create new ideas or products. So our goal as graduate study will be on these upper 3: analyze, evaluate, create. And of course, our foundations are built using remember, understand, and apply. So we will focus mostly on these top 3 skills: because this is a graduate level class, with the understanding that since this probability is so fundamental, we will also place some emphasis on apply, understand, and remember aspects of it, which are the lower aspects of learning, because having those concepts straight and concepts clear is what will help you analyze, evaluate, and create new products, or use this information in new ways for your research and analysis. So this is a graduate level class. Again, that means that how much you want to learn really depends upon you. The instructor or the classroom instruction is just the starting point of your learning. You need to go and dig deeper and learn more. And so there is some expectation of self-learning because you're graduate students. So though, keep those in mind. How much you want from this class really depends on how much you put into this class, because this is a graduate level class. All right. Assessment methods. We're going to use 3 instruments for our assessments. Assignments. These are worth 60% of your grade. Typically, you will get one assignment, either once a week or once every other week. Typically 2 to 5 problems depending on the complexity, and will likely extend concepts learned in the class. So most of these assignments will test you on things that we have taught in the class or we have done in the class, using a new data set or using, and saying like, what does this mean, or how do we extend what we have learned to something, so to the next step. The term project is worth 30% of your grade. It's a semester-long project on a data set and a topic of your choice. So this will be due finals week, but we'll have a midterm report as well as an early proposal on what you will be doing for your class. This again is something that you'll work on throughout the semester and try to apply all the concepts that we have run. So you'll be writing this in a journal format, and the paper will be formatted using another text processor called LaTeX instead of Microsoft Word. So you'll get some exposure to writing reports in LaTeX, which again is an industry standard software for producing some really stunning quality text. So I'll introduce you to LaTeX as we go along. Journal critique, this is worth 10% of your grade. Here you will read some papers, 1 or 2 journal articles, and do some critical evaluation of those journal articles. So again, this as being a graduate level class, if you're doing graduate study, you will be reading journal articles. So this is a way to get you started on that process. So assignments, mostly looking at the lower levels of learning, apply, understand, analyze concepts. Term project is looking at slightly higher levels, like analyze, evaluate, and create. And the journal critique is looking at analyze and evaluate portions. So as I said, we'll emphasize those higher levels of learning more so than the lower levels of learning. But a big chunk of your grade does depend on your lower levels of learning, because this is a fundamentals class. Class format, this is a 3-hour once a week class. I will tell you for sure, there is no with no uncertainty that listening to me lecture for 3 hours is boring and unproductive. So if you want to make this class fun, it needs to be a two-way street, a two-way interaction, or a two-way conversation between the students and the faculty. So please speak up, ask questions, answer questions, discuss concepts. So that is how the 3 hours are going to be exciting, and 3 hours are going to be useful for you. So again, so it's very, very important that I want to emphasize that you speak up and ask questions. There is no such thing as a bad question or a dumb question. All questions are valid. I plan to provide lectures ahead of time on Blackboard. I can't always guarantee this due to my schedule. In addition to my teaching, I direct a center, and I also have other meetings and travel that I have to do for my research. So And also I'm teaching this class for the first time, so I don't have a set of notes and lectures that are pre-compiled that I can just populate it with. But I will do my very best to try and get you the lecture ahead of the time on Blackboard so that you can have a look at it before you come to the class. And then rather provide a very large lecture slide deck, I will provide small chunks of lectures or small lecture chunks, and about 10 to 15 slides on a topic. And very likely we'll cover more than one topic in a class, depending upon the pace of the class. So whenever possible, whenever I have, put material ahead of the class, please go ahead and review that material. That will make things go a little bit more smoother and easier along the class. So roughly we'll use the first part of the class for lecture, and then the second part for hands-on exercises. So please bring your computers and with R installed. I will show you how R can be installed on your computers. And I'll put a video on that as well. So it should be fairly easy thing to do on Windows. Might take a little bit of time if you have a Mac or a Unix machine, but I recommend that you stick to the Windows machines for this class as it's required by the College of Engineering. So with that introduction about the class, let's go ahead and begin. So we'll start off by defining uncertainty and variability. I talked about uncertainty and variability several times during my earlier lecture, so you might be wondering what's uncertainty and what's variability. So uncertainty is the degree of precision or the lack thereof. Okay, so when we say we are uncertain about something, it means that we have incomplete information. Okay, so uncertainty can be reduced with collection of additional data. It may sometimes be even eliminated, but by and large, we can reduce uncertainty. There usually will always be some uncertainty left, because even though we might take more data, our instruments with which we take data are limited. They have some range of accuracy or some range of precision with which they can collect that data. So there'll always be some measurement error, which would mean that we can always be uncertain about the data, especially if we are collecting data at levels where the instrument accuracy is not very high. Then there is going to be greater uncertainty. So uncertainty is something that represents lack of information, and usually collection of more data helps us reduce that uncertainty. Variability is the natural variation in some quantity or parameters of interest. We really cannot reduce or eliminate variability. All we can do is variability can be characterized. Okay, so we can just characterize that variability. So what I'm showing here on the right are two graphs. The first graph here is showing data of monthly atmospheric carbon dioxide that was measured at Mauna Loa Observatory, which is in Hawaii. And the Mauna Loa Observatory has the longest record of CO2 measurements in the world. And here I'm plotting parts per million. This is the concentration of, so if I take million volume, million gallons or million liters of air, about 400 parts of that or 300 parts of that is carbon dioxide. So that's what this is saying. And on x-axis, I'm plotting the time from 1960 all the way to 2019. And you can see the concentration has gone up and up and up and up. But it does fluctuate. Okay, so it does go up and down a little bit, but in general, if I look from 1960 to 2019, the concentrations has gone up from about 310 parts per million to 400 plus, almost 410, 415 parts per million is where it is right now. And in the bottom chart, what I'm showing is the recent variability in the last few years, and you can see that the concentration goes up, goes down, goes up, goes down, and that blue line is the historical trend that is happening, or that is increasing throughout. So there is no uncertainty. We can state in no uncertain terms that the carbon dioxide concentrations in the atmosphere have gone up. Okay, so by collecting more data, we are being able to plot that trend, or we are able to see a trend in the concentrations. But on the other hand, if you look at data on a monthly, or a much short-term basis, you will see that the concentration goes up and down, up and down, up and down, up and down. So there is variability in that data, and that variability gets masked here, but you can still see that variability. But you can essentially say with very little to no uncertainty that the concentration of CO2 has increased. Of course, it is variable, but it's still increasing. Okay, so there is variability in the mean monthly atmospheric carbon dioxide concentrations, but there is little to no uncertainty that carbon dioxide concentrations have increased over time, over a long period of time. Okay, so probability theory is what we can use to describe both uncertainty and variability. So uncertainty is something that you can reduce with the collection of more data. If I just looked at 2060, I probably couldn't have told whether it's going up or down. But because we looked at data over a much longer time frame, we have collected a lot more data, we can say with a lot of certainty that concentrations are increasing. But variability still exists in that data, and we really cannot eliminate that variability. So a lot of times we don't make a distinction between uncertainty and variability, but it's important for you to know what uncertainty is and what variability is as far as your data sets are concerned. In terms of probability, we describe both uncertainty and variability using the same concepts or same models. So it doesn't make a difference, but it does make a difference for our engineering design, because one's something that we can eliminate or reduce with collection of more data, and the other one is something that we can characterize, but we can never eliminate or reduce it. So how do we deal with uncertainty or variability? Well, there is the first approach. The first approach is do nothing, which is ignore it. And we can get away with this if our uncertainty or variation is small. So if you know what the value is, and we say, okay, the value is going to be 50 whatever kips per square foot, say for some stress, and it varies, plus or minus 2 or plus or minus 2 KSF, then it's not a very big variation, so we can likely ignore it. The other approach that we can do is we see the variability, then we say, okay, we'll use a conservative value. Okay, and for example, the question then becomes, is that value truly conservative? So for an example, let's look at the probability of seeing a peak flow in Cypress Creek watershed, which is very close to Houston. And if I had looked at data before 2017, my most conservative estimate would place me at about 22,000 cubic feet per second flow rate. Okay, and based on that, if I had designed in 2017, we got Hurricane Harvey, which dumped about 50 inches of rainfall over 2-day, 3-day period in Houston area, and the flow rate because of that Hurricane Harvey in that watershed came to be over 30,000 cubic feet per second. So the peak flow was much larger. So a conservative estimate need not be conservative in the long run. So the key question that we ask, if we take and say, is the value truly conservative, then the question then becomes, what is really truly conservative? And sometimes, we can make assumptions. We can assume that there will be a significant pipe friction to reduce the flow rate through a given pipe. But because of mass balance, that would also mean that the flow in other parallel pipes is going to be much larger, because we can't lose mass. So if we make assumptions, we really need to question are these assumptions truly conservative? Like, have we captured all the variability that is likely possible? And in many cases, it is unlikely that we have captured all the variability that the system's likely going to experience, because a lot of our systems are out there in the open. They're sitting facing the nature, and that's very unique about civil engineering. So if we cannot ignore that uncertainty or variability, then we need to probably capture that. Okay, so if we are unclear whether the data that we have collected to our point can be used for future engineering decisions, then the question is our system going to see something that it has not seen in the past? And if the answer is yes, then that uncertainty must be described and taken into account when we are making our engineering design or performing our engineering analysis. Okay. Random events and random variables. Random events are events that cannot be predicted with a high degree of accuracy, and random events happen because of natural variability. We may have 100+ years of rainfall data. In many places, we have data for rainfall going a very long period of time, well into 1800s or mid 1800s. But even with all that data, we are still unable to predict the amount of rainfall that we're going to get next month. Okay, because the variability in that rainfall is very, very high. And also sometimes we have incomplete information. So a geotechnical engineer might go in and drill a borehole, and if we don't have a full depth hole, it's very hard to say where the bedrock is. Okay, so we can only estimate it based on what the soil looks like, what the other boreholes are saying, so on and so forth. But if you don't have complete information, that is a full depth borehole, you don't know where the bedrock is. So a random variable is a variable whose value is controlled by random events. So a variable whose exact value cannot be determined. Okay, so we can perhaps say the range of values is this. We can say most likely a typical value for it would be this, so on and so forth. But we really don't know what the true value is. So a variable whose value we are uncertain about. So again, I'm showing some soil shear strength data from that San Francisco site, and what we see here is that the very likely value is about 0.5, but you can see that the range of values can be quite a bit. It can be as high as 2, definitely very close to 0, so on and so forth. So a variable whose value we are uncertain about is a random variable. So the soil shear strength is a random variable because it depends on other random variables such as clay content, which varies in the site, soil moisture, the loading history on the site, all of which change the soil shear strength. So which in turn tells you that I can't predict this soil shear strength with a great deal of certainty, but I can certainly describe what is the likely range of values, what is the most likely value, and things like that. So we can characterize some aspects of that soil shear strength at the site or that random variable at the site, but we never can predict with high degree of accuracy what the number is going to be, because even if we predict, the most likely value is going to be 0.5, there is quite a few samples which greatly exceed that 0.5, so we could be way off in our prediction. So characterizing randomness. How do we characterize randomness? We characterize randomness by making repeated measurements. Okay, if the variable is deterministic, okay, then all repetitions will yield the same value. So the random variable is not random, but it's a constant. Excuse me. Repeated measurements are different most of the times because one, we have instrument limitations, and 2, we have natural variability in the system. So even if we have the perfect instrument, if I were to measure flow rate in summer, it's going to be very different from the flow rate in the winter. Same thing with wind loads. Like, if I measure the wind load in the morning, it's going to be very different from in the afternoon. And the same thing, like, it could be higher during certain times of the year and lower during certain times of the year. So repeated measurements are often different because either we have instrument or detection limitations, or we have natural variability in the system. If the variable is deterministic, then all repetitions will yield the same value. In that case, we don't have a random variable. So if repeated measurements yield different data, then we use then the variable is random. Okay, another word for randomness is stochastic. So we call that a stochastic variable or a random variable. And the idea of characterizing randomness using repeated measurements is what's called as the frequentist approach, because we measure in repeated times and see with what frequency does something occur, recur in our system. So repeated measurements is what is referred to as frequentist approach, and that's another word for randomness or stochastic approach. Randomness, the stochastic approach or the frequentist approach, where we are making repeated measurements, is not the only way in which is not the only type of uncertainty. There can be other types of uncertainty. So variability that's arising due to inherent randomness is also called the aleatory uncertainty, and or stochastic uncertainty or objective uncertainty. And because when we make repeated measurements, it better characterizes the data. But there is also uncertainty due to limited knowledge of the underlying processor or certain vague information. So things like short or tall, that is a very subjective decision. So if I look at a man whose height is 5 feet 8 inches, which happens to be my height, there are many countries in the world where my height is above average, certainly, and then there are many countries in the world where my height is below average. So there are certain parts of the world where I probably would be considered tall, and there are certain parts of the world where I probably would be considered on the shorter side of based on my height. So it's a perception issue. Just to give you an example here, NHL Commissioner Gary Bettman, he's about 5 feet 7 inches, an inch shorter than me, but there are many countries where that height would be an above average height, and we also perceive him to be much shorter in this picture because he's standing to a person who is much taller than him. So there is some subjectivity that is based on perceptions, and there is uncertainty because of that subjectivity, but that's another type of uncertainty. We're not going to deal with this type of uncertainty in this class. We'll largely be dealing with stochastic or objective uncertainties, where a lot of our where repeated measurements either help us eliminate that uncertainty or minimize that uncertainty or better characterize that uncertainty. So characterizing uncertainty requires data, and data are collected either through observations or conducting an experiment or doing modeling studies. So those are the three different ways in which we generate data as part of our, in most civil engineering problems. So uncertainty and variability are inherent in all civil systems. We have uncertain loads on structures, we have traffic variability, we have incomplete information on soil properties, variability of flows and contaminant concentrations. When uncertainty cannot be ignored, it must be characterized. We need to properly document what we collect, because the future use of that data for engineering decisions is unknown. Natural variability and certain types of uncertainty can be reduced by making more measurements, or at least we can better characterize that uncertainty. And that type of uncertainty is called aleatory uncertainty, stochastic uncertainty, or objective uncertainty. And repeated measurements to reduce uncertainty or at least better characterize uncertainty is referred to as the frequentist approach, because we are using the frequency of measurements, seeing how many times does a value repeat itself, like, for that random variable. Of course, not all uncertainty is can be solved using frequentist approach. So when people say soft soils, low traffic, exceptional drought, severe wind loads, there is some subjectivity associated with those definitions. Like, what's severe in one location need not be severe in another location. Similarly, an exceptional drought can mean different levels of moisture deficits in different parts of the world. What's a soft soil? It really depends on what you're using that soil for. A hard soil for agriculture need not necessarily be hard enough to construct a road on it, or put a pavement on it. So again, so that's a subjectivity. Low traffic in Lubbock can mean something very different from low traffic in Houston, which can mean very different from low traffic in Muleshoe. So again, what's low traffic can be very subjective. So those types of subjective uncertainties, I just want to make you aware of those types of subjective uncertainties, but that is not the primary focus of this class. In this class, we'll be mostly looking at objective uncertainties, or uncertainties that can be minimized using repeated measurements. So that is a broad introduction to our class and introduction to the concepts that we'll be studying in our class. In the next lecture, I will continue on with our discussion of uncertainty and variability, and then introduce you to R programming in the next subsequent lectures.